Okay, so picking up where we just left off, we're going to talk about blood moving from the systemic to the venous side of circulation, and 4 major changes take place. Okay, number 1, the number of veins decrease progressively the further we go away from the capillaries, the less veins there are. Okay, so number 1, the number of veins decrease progressively. So as we go from this capillary network, so on the systemic side, into the venules, as the flow goes to the venous side of circulation, the number of veins decrease progressively, right? Like I said before, we have a vast network down here, so we're starting to get into the larger vessels again, so those numbers are going to decrease. 2, the thickness and the composition of the walls change. 3, total cross-sectional area decreases. And 4, the velocity of flow starts to increase again, so it will increase. Okay, we'll go through those again. 1, the number of veins decrease progressively, so this means the further we go away from the capillaries, the less veins there are. 2, the thickness and the composition of the walls change, so the walls are different in those vessels compared to the systemic arterioles and capillaries. 3, total cross-sectional area decreases, and 4, the velocity of flow increases. At any one point in time, the majority of the blood in our system is on the venous side of circulation. So 60 to 70% of our blood is always on the venous side of circulation. So it's not split 50-50 as you would think. Oh, well, half of it is bringing blood to the area and dropping off, and half is on the venous side of circulation, bringing it back to the heart. It's actually not the case. There's actually 60 to 70% of our entire blood volume is on the venous side of circulation. So let's make 2 quick summary statements about that intro of what I just did the last couple of videos. 1, in a healthy human being, the volume of blood is constant. We can only circulate what we have faster and alter what's going on anatomically, right? We can't really go to like a gas pump and pump up and give ourselves more blood on a day-to-day basis. So we can only pump around what we have faster or shunt it from one area to another area. In order to increase blood in one area, we must borrow it from another area. 2, velocity of blood as it circulates through the vessels is determined by 2 factors. 1, output of the left ventricle, and 2, the amount of resistance that exists to flow by the vessels themselves. So the elastic tissue of the arteries allows us to store energy in its walls and helps aid in moving pulsatile flow to smooth flow. And velocity increases dramatically as blood moves into the aorta and then decreases as blood moves to the arterioles. Pressure drops from the beginning of the arteries to the end of the arterioles as blood enters and exits because pressure is an energy form. Energy we need to overcome. It's the energy we need to overcome the resistance to flow and in order to maintain steady flow throughout the vessels. All right, so those are some summary statements of what we have talked thus far. Okay, so now that we did our intro to the heart and our intro to systemic and venous side of circulation, we are going to get into electrophysiology of the heart. Okay, so let's move into that. And here is what's called an ECG, right? So an electrocardiogram, and an electrocardiogram represents 2 things. 1, electropotentials, and 2, the flow of electrical current. Okay, so this just isn't in the myocardium of the heart, right? We can find electropotentials in any tissue that can be excitable, nerve, skeletal muscle, heart, etc. Right? So electrical potentials are dependent upon potential difference. What is the potential difference? Potential difference is the different charge inside of the cell relative to the outside of the cell. This is true for any excitable tissue. That potential difference is dependent upon an unequal distribution of ions across the cell membrane, right? So where does this ring a bell from? Neuromuscular physiology, where we have the difference in sodium and potassium on the inside and the outside of the cell. We have a stimulus that comes down, an action potential that alters those gates and alters those ions that are being distributed. It's the same thing within the heart. Sometimes slightly different with the level of the millivolts and what's going on, but it's the same exact concepts with regards to electrical potentials and the differences of distribution of ions across the cell membrane. Right, so electrical potentials are dependent upon potential difference. Potential difference is a different charge inside of the cell relative to the outside of the cell. Okay, so let's talk about resting membrane potential. Resting membrane potential in the heart is negative 90 millivolts. So just like we talked about skeletal muscle tissue, there's an unequal distribution of ions across that cell membrane. Negative 90 millivolts is maintained by that electrochemical gradient. The membrane is selectively permeable to sodium and potassium, right? Concepts that we've already talked about before. So, to refresh, let's go. There's a large amount of potassium on the inside of the cell and a small amount on the outside of the cell, right? So here we have the inside of the cell, and here's the outside of the cell, extracellular space, and then here we are in the cytoplasm down here, okay? So we have a large amount of potassium on the inside of the cell and a small amount of potassium on the outside of the cell. We have a large amount of sodium on the outside of the cell, and then we have a small amount of sodium on the inside of the cell. We have a large amount of negatively charged anions on the inside of the cell, right? So we have a lot of anions on the inside of the cell, and we have a small amount on the outside. And then we have a large amount of chloride ions on the outside of the cell, okay? And those are negative. So we have a lot of negatively charged chloride ions on the outside of the cell, a lot of negatively charged anions on the inside of the cell. So for every 100 potassium ions moving out of the cell, we allow 1 sodium into the cell, right? So we leave those negatively charged anions behind, giving us a negative number, a negative resting membrane potential. Okay, so let's go over that again. We have a large amount of negatively charged anions on the side, and we have a large amount of positively charged potassiums on the inside of the cell. Now on the outside of the cell, we have a large amount of negatively charged chloride ions and a lot of positively charged sodium ions. However, for every 100 ions, 100 potassium ions, we are moving out of the cell. Right? So that's something positive. We're moving something positive out of the cell, but what are we leaving behind? We're leaving those negatively charged anions behind, right? And then we only allow something positive, 1 molecule in exchange. So naturally we want 100 potassiums on the outside of the cell, a resting membrane potential, and 1 comes in for every 100 potassiums moving out. So what happens? We have all those negatively charged anions, which gives us that negative resting membrane potential. Okay, because we are moving a lot of something positive out and leaving negatively charged particles behind, giving us a resting membrane potential of negative 90 millivolts. Right, so what else is going on at that time within the cell during resting membrane potential? We have active transport, which is our sodium-potassium exchange pump. It's also taking place, right? So here we are moving against the gradient. So remember, when we move against the gradient, it requires ATP. So for every sodium now we are moving out of the cell, we move 2 sodiums back in. But we are exchanging 3 sodiums out of the cell going against its gradient because we don't have much in there anyway. That's why it's going against its gradient. But then we're only bringing 2 potassiums back into the cell, which are positive. So again, that is further leading to the resting membrane's potential's negativity there.